Log on, tune in, find out. Another good idea from Cambridge.
So I'm an oceanographer at the University of Washington, the School of Oceanography, and this work I'm collaborating with Kathy Kelly, who's at the Applied Physics Lab at the University of Washington, and Suzanne Dickinson, and Julie McLean, who's at Scripps Institution of Oceanography, Eric Greiner, who's at Mercator Ocean. Actually, I think he's at CLS, but he's in France, and Dimitri Menemenlis, who's at JPL in Pasadena. And you'll see why all these people's names are on here, because I use various model outputs. Are the lights good? Can you see this well?
It's not particularly bright, is it?
Wonder if
No, change it.
turning off the
Oh, okay.
There you go. Is that better? Yes. Yeah. So I advertise this as estimates of the oceanic heat budget in the Gulf Stream, and what I want to do before I start talking about that is just to talk about how currents like the Gulf Stream and the Kuroshio are represented in the current generation of climate models. I thought it would be useful for this group to think about this a little bit, since much of the memory in the mid-latitudes comes from these current systems and heat storage. So you guys have all seen this picture before, I'm sure. The ocean conveyor, which in a very idealized framework. And in particular, what we're going to be looking at is the warm water path in the Atlantic. And you can already see that this is not very realistic in terms of where the Gulf Stream really hugs the coast up until about Cape Hatteras, and then shoots off offshore, and then turns north into the North Atlantic Current. And what I wanted to point out initially is that it is in the region of the Gulf Stream, which is here, and the Kuroshio in the North Pacific, where you get a huge release of heat from the ocean to the atmosphere. So there is heat being moved poleward in the North Atlantic, but there is a lot of heat exchange that happens in that region. And I think we tend to forget about that when we're thinking about the Mariana overturning circulation. So, and in particular, if you look at, this is from Trenworth and Karen, these are the different oceans, meridional heat transport. The total is in the black, the Pacific is the green, the Atlantic is the blue, and the Indian is the red. So we're going to focus on the blue curve in the Atlantic, and in particular, between here and here, 30-some north to 40-some north, about 0.2 petawatts, or actually about half a petawatt is lost from the ocean to the atmosphere at that latitude. So you can see there's a big drop-off in the oceanic meridional heat transport. And if you do a box over the Gulf Stream, there's about 2 petawatts of energy that's released in the Gulf Stream, in the mean, from the ocean to the atmosphere. Now, if that much heat is lost, it has to be brought in from the sides by the ocean, of course. There's no other source of heat within the ocean, so it's an effective process. So if we look at mean biases, and this is in CCSM3, which is pretty typical climate model, run at 1 degree nominal resolution in the mid-latitudes. They tend to have higher resolution in the tropics to be able to resolve the equatorial waveguide. So hopefully you guys can see this well enough. This is the Kuroshio, and this is the Gulf Stream. The top row is the fully coupled simulation, and this is mean SST bias. And the bottom row is an ocean only, driven by climatology of atmospheric forcing. So in particular, you can see in the Gulf Stream that the temperatures tend to be too warm upstream and too cold downstream and over the North Atlantic Current. So what's happening is, although the separation latitude is not really so bad in these climate models, the heat isn't pulled out into the interior. It's really kept up against the coast, and then you have a cool bias downstream. And these are big biases, right? This is 10 degrees C here. So, you know, it's not a small bias, it's a big bias. Maybe if you average over the region, you get a smaller bias, but it is a rather large SST bias. And because it appears at a slightly lower magnitude in the ocean-only simulation, this is really an ocean problem. It's not an atmospheric problem. And it has to do with the fact that we're not really adequately resolving the dynamics in that region. So just to show you that this is not something that's special to CCSM, I grabbed this out of a paper by Delworth, and here's the SST bias in the Gulf Stream in the GFDL model. Once again, you can see the cold bias downstream and the warm bias upstream. So this is sort of a consistent picture of models run at 1 degree resolution. Okay, so now if we ask, what does that have to do with variability in the climate system? Maybe if the mean is biased, then but the variability might be okay. So Young-Oh Kwon, who's at Latoul, and I did a study of the interannual variability in the Kuroshio. And what we found was that if you compare against observations, here's using a 27-year satellite record of SST. Here's the interannual variability, so just the standard deviation of annual mean anomalies. So here it is in GRIST, and here it is in CCSM3. And you can see it's actually much larger in CCSM3 than it is in GRIST. So this is a case where the climate model is actually overexpressing the variability. And the reasons for this is because the mean bias in the current, and that the heat tends to be stored in too shallow. It doesn't go deep enough. And that paper should appear in Journal of Climate soon. Okay, so this is not a great data set for doing this, but I wanted to make a picture for the Gulf Stream. This is for ERA 42 degree SST resolution. This is observations, and this is CCSM3. And I'm going to redo this with the GRIST data set. I just haven't had a chance to do that yet. But once again, they're suggested that in the Gulf Stream North Atlantic current system, the interannual variability is overexpressed in the climate model, probably because of the mean biases in the system. And I would like to explore that more later, but not. And once again, if we look at GFDL, this is the observation. So this is basically the same data set that I did the comparison of. And hopefully you can see there is a fairly large interannual bias in the GFDL model as well. And this is a paper by Knudsen et al. So I think it's important to recognize that the biases that we see in climate models, it's not just a mean bias. It also affects how the ocean, the SST variability in the mid-latitudes. So I think I said that. Most of the IPCC models that in the AR5 will be run at 100 kilometer resolution, nominal resolution at mid-latitude. So this kind of bias is going to persist in the next round. For the most part, there are some higher resolution modeling going on. And the other thing to keep in mind is that climate models tend to show large decadal variability in the subpolar North Atlantic, which connections to the Gulf Stream, with the mechanisms of that variability dependent on which model, which specific climate model you're looking at. And they tend to be stronger than what we can tell from the observation. So it's just sort of a cautionary note on trusting some of those modes of decadal variability in the climate models. So that's all I'm going to say about that, but I just thought that would be useful for people in this institute to keep in mind when we're thinking about the ocean's role in predictability decadal variability. Okay, so now I'm going to get into the real part of my talk, which is the role of the Gulf Stream in heat transport and heat storage. So the questions I wanted to ask are, what role does oceanic geostrophic advection? So I'm not talking about Ekman advection, I'm talking about ocean dynamics as opposed to a passive advective response of the surface layer in the Gulf Stream and the North Atlantic current, although I'm not going to talk very much about the North Atlantic current on interannual timescales. How well can we estimate this, and what processes control the budget? So what I wanted to do when I decided to attack this problem is to look at models where the Gulf Stream was well represented, because I knew about the problem in the low resolution models, and I wanted to make sure that at least the mean Gulf Stream looked right, and then we would look at the variability. So I took 4 models, kind of a crazy thing to do, but involved a lot of data crunching, and I'll tell you a little bit about all of these. And I don't know how familiar you are with the observational record in the ocean. We're used to looking at SSTs and the Levitas heat content curve, but the real workhorse of variability in the ocean for assimilation is the altimetry record that started in October 1992, and it's still going on. hopefully in perpetuity. And that's where the sea level record comes from that we're used to thinking about from the early 90s on. So this has nominal resolution. I think they give it to you on like a half-degree grid, but it probably is 100 to 200 kilometer grid, but you get some of the eddies and the variability really quite well from a VISO. So that really is, when you look at assimilating ocean models, they most often use the sea level as the simulation. So the first model is a North Atlantic simulation done by Julie McLean. It's the Parallel Ocean Program, POP, which is out of NCAR. It was actually driven by daily Navy forecast winds, but it's purely prognostic. There's no assimilation in that one. 1/10 of a degree resolution. I had 21-day samples. And it's just a North Atlantic simulation, so it's relaxed to observations at 72 north and 20 south. So it actually gets a reasonable deep structure of the circulation because it's forced to be like that at the north. And it went from 1980 to 2000. Mercator has several simulation products, and I used one that started in 1992 at the beginning of the altimetry record through 2003, 1/3 of a degree resolution. This one, however, nudges to both in situ sea surface height and sea surface temperature, which, as you can guess, makes doing a closed heat budget difficult, and it's driven by daily ECMWF ERA 40 wind. The next one is ECHO 2, and you may have heard of ECHO. There's several different versions of it. This is out of JPL, Dimitri's. I should say Eric Greiner gave me this data, and Dimitri gave me this data. This one uses NCEP daily forcing. It has 18 kilometer resolution, uses a Green's function assimilation, and it goes once again from the beginning of the altimetry record. This Green's function assimilation, basically he does a bunch of runs with different parameters and then creates a composite simulation using all those different runs. So this one, the heat budget does close. And it's sort of a poor man's assimilation. It's not a full adjoint, or it doesn't nudge everywhere. And then this diagnostic model basically uses daily NCEP and ISCIP forcing. It's a low resolution, but it gets its velocity directly from the sea surface height with the prescribed vertical structure. And this is work that Kelly and Dong did, and I use this kind of as a reference. Okay, so the caveats for the estimates. I think I already said this a little bit. The POP run, it's fully, pretty close to eddy resolving. I think we could debate that. The interior fields and sea surface height are not constrained by observations, except for at the northern and southern boundaries. But it is interesting that the model SST can be out of sync with the atmosphere because it has its own intrinsic variability. So it's not necessarily going to look just like the observation step by step. The North Atlantic one, as I said, it has interior sources of heat and salt, which is not physical. And the other thing is that the output wasn't given to me on the native grid, the native model grid, which is a big problem. I banged my head about getting this budget to close, and I finally did. We had a tiny little leak in the corner of our box, and the volume conservation was off by about 4 sphaerdrops, which is bad. So I'll show you that I can close it now. And then ECHO 2, it's not entirely consistent with observations, but it does, with eddy permitting, and does a pretty good job. And then the diagnostic muscle also doesn't conserve volume, so that makes it difficult to really close the heat budget.
Excuse me, Glenn.
Yeah.
When you say the model at SST is out of sync with the atmosphere, you say from step to step. How big is the time step, and how much is a lag? I mean, it's quite a bit of persistence in SST. So, does it really matter?
Oh, what I mean by that is if, say, the Gulf Stream path, and I'll show you that it doesn't track the observation. So if you think that there's a large temperature gradient across the Gulf Stream, and if in the observations the Gulf Stream is, say, 50 kilometers north of where it is in the model, then the SST in the model and the air temperature will not be really compatible in a sense. Does that make sense?
Yes.
Okay, because it goes from, there's a big 4-degree temperature in the mean, temperature gradient across the Gulf Stream, and at times it's much bigger than that. So The air temperature, of course, is controlled somewhat from the atmosphere, but it also adjusts to the SST. So they're not really, that's what I mean by not compatible. If it was run fully coupled, then it would be okay. Okay.
Thank you.
Okay, so here's the mean surface velocities from POP. I've just given you the North Atlantic current is up here, and I pointed out just because it's really hard to get the North Atlantic current in the right place. And you can see that POP does an awfully good job compared to mean climatology of surface currents from Makumenko and Mueller in 2019. So the Gulf Stream is in the right place, the North Atlantic current is in the right place. It looks pretty good. Okay, so now to remind you what the real ocean looks like, I just grabbed this off the red. This is a false color sea surface temperature image for one day, and this is the Gulf Stream. And what's interesting to remember is that there's actually a warm core of the Gulf Stream that goes into the interior. It's kind of amazing structure when you think about it. And if you look at models, here's a 100-kilometer resolution simulation, and here's a 10-kilometer resolution simulation. And you can see how different it is structurally. Here's this weaker gradient here, and here's the warm core that you see in POP that you don't see in the climate. Okay, so now I wanted to evaluate what the Gulf Stream looked like in each of these simulations. And this is basically what I did to find the path of the Gulf Stream is I used a method of Kathy-Kelly to fit the sea surface height to a error function to find the center and the height difference across the Gulf Stream, and so that defines a path and a height difference. So these are 21-day samples of path, and these are monthly samples from satellite observations. And in some ways, they're pretty similar. The amount of energy is pretty similar, but you see big differences between the two. You see that the model tends to be pinned right here, and you don't see that in the observations. There also seems to be a lack of variability right here, and that is about where the New England seamounts are. And there also seems to be a bit of a bimodal thing going on here that, once again, you don't see in the observation. So there are details that are quite different. If you did the RMS sea surface height variability, you would say, wow, that looks pretty good. But on monthly to interannual timescales, it's not really exactly, it's not so much that it's not tracking it, from time step to time step, but there are structural differences between the two. A little bit disconcerting because you'd like it when you go to high enough resolution that it would look pretty good. That's what it is. So here's the mean path from all the models, and here's the mean height difference. So the height difference, once again, if the Gulf Stream is geostrophic, will give you the strength of the current. And you can see that all the models show too much strength upstream relative to the observation. So this is a VISO, and then these are the other three models. And the path is pretty good, actually. It's really not, the mean path is actually not so bad. This is an outlier that I should have gotten rid of. So we can ask, how does the height difference and the path track with a VISO on interannual timescales? So I removed the seasonal cycle and then low passed it. So this is the path latitude and this is the height difference. And I averaged between 72 x and 50. And the correlations are down here. And for Mercator, remember, it assimilates sea surface height. So you'd hope that it would be pretty good. It's highly correlated in path. This is the significance level. And in height difference, 95%. And then Echo 2, once again, reasonably, it is correlated, weakly correlated in the height difference. And in POP, is not correlated. So POP does not show the same year-to-year variability in height and path. So that suggests that there's a lot of intrinsic variability inside POP. Okay, so we can make an overall picture of the interannual standard deviation. Here's a VISO, here's Mercator, here's Echo 2, and here's POP. You can see this too much upstream variability in Echo 2 and Prof. Mercator is actually doing pretty well, but once again, it assimilates. So these are the challenges of trying to accurately represent the Gulfstream models. So my first conclusion from this analysis is that POP's interannual variability does not follow the observations, which indicates that there's intrinsic ocean variability within the Gulfstream system. The Gulf Stream tends to be too strong upstream in eddy permitting models, and the Gulf Stream is qualitatively correct for models that assimilate and permit eddies. Now, it is interesting to note that in the Curcio, you see kind of a similar sort of result with this too strong upstream. You get this permanent meander in many of the high-resolution simulations fairly far upstream that you don't see in observations. And it kind of has this bimodal behavior. So it's probably not something unique to the Gulf Stream. Okay, so now finally to the heat budget, which was the promised thing. So basically what I did is I defined a box. This is the Gulf Stream box, and there's a North Atlantic Current box. I'm not going to really talk about that here. And then performed a heat budget over that box. So the heat budget, basically what I did is I defined the heat storage rate or heat content variability, the integral over that volume down to a certain depth of the temperature, and take the derivative of it. And then a horizontal heat transport convergence, so that's separate from the vertical heat transport convergence. Should have taken that out. And the net surface heat flux over the area. Averaged over the boxes, I remove the seasonal cycle, I low and high pass for interannual and monthly signals, and positive indicates heating of the ocean. So here's the net surface heat flux, kind of to start with. The first thing to note is that the surface fluxes are not correlated between the models, which is a little bit surprising because it's forced by the atmosphere overhead, but once again, the model SST is not exactly the observed SST. So you're going to get some adjustment. The standard deviation in all the models is, nominally similar. The mean out of that box is about 90 watts per meter squared. And for the Gulf Stream region, that's equivalent to about 0.2 petawatts if we add up all the area. The atmospheric specifications are similar in all the models. They're all using observed or NSEP winds, but the turbulent fluxes are determined partially by the model SST. So there is coupling, and that's kind of what I was talking about earlier. So if you think about what the sensible heat flux and the latent heat flux looks like, there's a model SST, and then there's the atmospheric specification, model specific humidity saturation, and the atmospheric specification. And so if and this of course depends on the sea surface temperature. If your sea surface temperature is a little bit off, it's gonna change the surface flux from what the observed flux would be. And so that's what's going on here. Which suggests I really should be doing this in a coupled framework, and then I get nervous. Okay, so this is the answer, basically. And this is the extension of Dong and Kelly. And their model only went down to 800 meters. The heat storage rate is in red. The net surface heat flux is in blue. And the horizontal heat transport convergence is in black. And for the most part, the heat storage rate, which is red, and the heat transport convergence in black track each other and are correlated. So the heat storage rate is being controlled by horizontal heat transport convergence. And that was the conclusion that Dong and Kelly came up with. Now, the budget's not closed, and then the question is what happens below 800 meters? And is 800 meters the right place to integrate to? So we can go ahead and look at it in the other models. So this is Mercator integrated down to 800 meters. And once again, the heat transport convergence dominates, but it's not really correlated with the heat storage rate. And this has to do with interior sources of heat and salt. It messes up the heat budget.
It almost looks like it's anti-correlated.
Yeah, I know. So, I mean, maybe in retrospect, I shouldn't have looked at Mercator, but, it's easy to determine that in hindsight. But The heat budget is pretty sensitive to how you do it. Anyway, I mean, not how you do it. It's sensitive to closing it. And if you don't close it, you get really bogus answers. Okay, so this is POP. And remember, this is horizontal heat transport convergence. So I'm not plotting the vertical part. And the vertical part would be the residual. So here's the heat storage rate. And here's the surface heat flux. And the heat transport convergence and the heat storage rate are correlated. The heat transport convergence is much bigger than the heat storage rate. But once again, the horizontal transport dominates. And what this indicates is there's a lot of vertical pumping going on in POP that is bringing heat from the top part of the water column at depth and then bringing it back up again. So if you look at heat storage rate from all the models, you actually get pretty similar values. This is in watts per meter squared for standard deviation, from 31 for the diagnostic model up to 42 for Mercator. Now, if we go down to the bottom, we get slightly bigger numbers, but not hugely bigger numbers. And I'll show you some of the top to bottom heat budgets. But remember that the standard deviation of the surface heat flux was more like 10 to 15, and the mean surface heat flux is 90. So this is a significant fraction of the mean surface heat flux coming out of the thing. So you can store a lot of heat in that fairly small region, and it can be transported laterally, and maybe some out the top.
Question.
Yeah.
Can you remind us which one of these models know about subsurface temperatures? Which ones are assimilating subsurface information? Which ones don't know about it?
So Mercator does assimilate in situ, and Echo, I don't know.
Probably does.
It probably does, but it is interesting that most of these models rely most heavily on the sea level. You took the sea level away, you'd get very different answers. So, and then POP, of course, has its own temperature variability at depth. But it is an interesting question, because when you look at the top to bottom, the fact that POP has these huge vertical excursions or vertical movement of heat that the other models don't show, I think tells us something. Okay, so the upper ocean heat storage rate is controlled by advection. The interannual signal is model dependent. Too bad, but it's true. Variability in heat storage rate is a significant fraction of the mean net surface heat flux.
Excuse me, Luann.
Yeah.
Can you give a little more detail on your filtering? I mean, was it a band filter, or was it just, low and then high, or?
Yeah, basically all I did, very simple, being not that good at filtering, is I removed the seasonal cycle with a couple of harmonics. I low passed 1 year to get the high, and then what's left, to get the low, and what's left is the high. So it's very simple. And you can see some annual signal still in there, or nearly annual signal. It's not like there's a peak at 1 year. It's a pretty red spectrum. I played around with doing 2 years, 3 years for the low pass, and the numbers get a little smaller, but other than that. Okay. So first of all, then I thought, well, I'd better go to the bottom to see what happens. And there was a couple of concerns that whether I was actually closing the heat budget and whether I needed higher frequency sampling than 21 days or monthly. And luckily, I just about closed the heat budget using the 21-day samples. The volume conservation was to within 0.1 sphere drops, which I could live with. So that allowed me to have confidence with moving forward. Okay, so if you look at the Mercator top to bottom heat budget, it doesn't close, which once again we kind of suspected. Volume non-conservation of about 5 sphere drips, and that probably has to do with the fact that I didn't get the output on the model native grid, more than the nudging. The heat budget doesn't close because of nudging, but having it not on the model native grid is a big problem. Okay, so now let's look at the POP heat storage rate and the heat transport convergence. You can see that down to the bottom is the red, and to 800 meters is the black. And they're about the same size and fairly well correlated. So that says that most of the interannual variability is carried in the upper 800 meters, not carried at the bottom. So that vertical pumping is just moving things up and down. It's not really changing the overall budget. And here's the heat transport convergence, which are correlated, but it gets smaller if you go all the way down to the bottom. And then Mercator shows similar, if you go down to the bottom, there actually isn't that drop off in the horizontal heat transport convergence, which I talked about, that you don't get that vertical pumping that you get in top. And that's somewhat true in echo as well. Heat storage rate to the bottom is green. The heat storage rate to 800 meters is red. And then I threw in here, the black is the heat storage rate to 100 meters, which tends to be a little bit more correlated with the surface flux rather than the heat transport convergence. So if you don't go very far down into the water column, it looks like the surface flux. I'm going a little fast, so please stop me if you have any other questions. Okay, so then I thought, okay, what is the depth dependent of the heat content variability? So I defined the standard deviation of heat content by a vertical, cumulative vertical integral of the temperature. So this is, it's 0 by definition at the top, and then you accumulate it as you go down. And then the blue line is the high frequency, and the black line is the low frequency. So, what's that?
But what's the difference? Where does it split between high and
At a year.
low? Okay.
So remember, I have monthly samples. So, so pop and echo actually look kind of similar in the high frequency. There's a little bit of a break here. Accumulation rate goes down. And in the low frequency, Mercator is obviously doing funny things because of the nudging. Pop, once you get to 800 meters, you can tell that you're not accumulating a lot more variability in the heat content. And that's true of echo as well. So for low frequency, most of the variability is carried in the upper 800 meters, and the high frequency is mostly carried in the upper 200 meters. So, which once again makes sense, that the high frequency would be responding more quickly would be responding more in the upper ocean. So the heat content variability on interannual timescales is carried above 800 meters, and the vertical divergence can be large if the eddies are resolved. Okay, so now put in a little bit of model. Okay, so let's look at the high frequency versus the low frequency variability, and reminding you what this heat content is and the net surface heat flux. So at high frequencies, we might expect that the ocean is slave to the atmosphere. Just going to look like this. H would lag the surface flux, but what depth would we expect that this would hold? And you know, this is probably not the perfect model, but if we look at the correlations of the high frequency heat content to the surface flux, remember, it's a cumulative heat content, remember. This is the significance level. So here's Mercator, here's pop, and here's echo. And in echo, you actually see a significant correlation at above 100 meters with the heat content lagging the surface flux by a month. Pop, there's a suggestion that it could get there. I mean, Mercator, there's a suggestion that it could get there. For pop, you don't see it at all. And once again, that's probably the lack of compatibility between the atmospheric air temperature and the sea surface temperature in the model.
Those correlation coefficients are less than 0.2.
Yes, they're not big. I agree, totally small. I mean, this is the significance level, but they're not very big. I totally agree with you. If you look at the interannual, it's a little bit more convincing, although the significance level goes up quite a bit. Okay, so now it's more interesting to look at the interannual stuff. And so at low frequencies, we found that the heat content was controlled by advection, but there was a little contribution by the net surface heat flux. And Dong and Kelly suggested that the net surface heat flux is going to be given by some atmospheric random component and then a relaxation of the heat content down to some depth, and they said to 800 meters, with the net surface heat flux lagging H by 3 months. So basically this says that when the ocean is warm, it's going to flux heat out to the atmosphere. And the question we wanted to ask is this, does this apply in these full models? And for the most part, it does. And here's the significance levels. Here's the correlation. Once again, just barely above significance. But you can see that you get significant below about 300 meters. You get a peak at about 400 or 500 meters in Mercator and in Echo, where the surface flux is negatively correlated with the heat content, and the surface flux lags the heat content by about 3 months. So this is borne out by these full models. POP, you do get a significant correlation at depth, but once again, this lack of compatibility between the model state and the atmosphere overhead makes this a little bit less certain. And the heat content leads the surface flux by 6 months. It's just a little bit strange. So then if you ask how much surface flux is explained by the heat content, somewhere around 10 watts per meter squared of the 15 or so watts per meter squared of interannual variability is explained by changes in the upper ocean heat content. So, I mean, this is small compared to the errors in surface fluxes, but it is significant when you compare the interannual variability in the heat content. So I think I'm going to finish too soon, so that's not bad. So at low frequencies in the Gulf Stream, the surface flux is explained in large part by the upper ocean heat content, with flux lagging the heat content by about 3 months, and then explains about 10 watts per meter squared of the variability in the surface flux, about half or a little bit more than half. Now, what causes this 3 months? And that's next on my agenda to figure out. And I'm guessing that it has something to do with reemergence. The fact that you store the memory of the climate system from the last year in the upper 300 or 400 meters, the mixed layers get deep and then it comes back out again. But I haven't really shown that. I need to look at winter versus summer correlation. Okay, so just to summarize what I learned from this study, I learned probably I shouldn't have used Mercator to start with, but that interannual heat storage rate to 800 meters captures most of the interannual variability. On interannual timescales, the heat content is controlled by advection with a standard deviation of about 40 watts per meter squared, which is equivalent to about 1/10 of a petawatt. And on interannual timescales, the net surface heat flux damps the heat content down to about 400 meters, with the heat content leading the net surface heat flux by about 3 months. And the heat content variability explaining about 10 watts per meter squared of interannual net surface heat flux changes. The heat budget doesn't seem to be controlled by, intrinsic ocean variability in the models. So it's not easy to pull out a wind-forced control of the heat transport convergence. And in particular, I didn't show this because there were no correlations, that the strength or the path of the Gulf Stream doesn't really explain the heat content variability. So my guess is that it has to do with this storage in what some people would call the mode waters down to the depth of of maximum mixed layer depth that then reemerges again. And that is likely somewhat independent of the strength of the Gulf Stream. And then just some quick comments on the different models, which I've said repeatedly, that when you look at these high resolution simulations, there is a lot of coupling, at least local coupling, between the ocean and the atmosphere where the sea surface temperature gradients are so big. And that makes this heat budget a little bit hard to interpret because the ocean and the atmosphere are not compatible with each other. Not having the output on the model native grid is a big problem, which I didn't really appreciate before I did this. Echo 2 would be my favorite of all of them in terms of how well it does reproducing both the Gulf Stream and that it's consistent with the atmosphere overhead. And that this sort of general conclusion that going to higher resolution unfortunately doesn't solve all problems, because you get these funny things like the interannual variability is too large upstream, you get sort of a bimodal behavior, and you may not have the right physics in the ocean. Oh, I did have one more thing to show. So I wanted to show you, just to think a little bit more about high resolution simulations. I'm going to show you a little movie to think about the deep water path. And this is partly for you, because it's a high resolution movie, and you've probably seen this, Robin. And basically, this was run by Frank Bryant, Matt Maltred, and Cinta Peacock. I was actually on the proposal, but just because they needed a university partner, I didn't really do anything. They ran it in Oak Ridge. It's a 10-kilometer simulation, 100 years long, which is pretty unusual when this was run. And what I'm showing you is CFCs, chlorofluorocarbons, at 1,600 meters. So this is well below the Gulf Stream. And does everyone know about CFCs? Anyone not? Okay. So chlorofluorocarbons are, they're the ozone-killing chemical in the atmosphere. But once they get into the ocean, they're inert. And because they have an exponentially rising atmospheric concentration over time, you can actually tag the water with an age from CFCs. So people like to observe CFCs because it gives you some idea of how long it's been since that water has been at the surface. So the CFCs go into the ocean at high latitudes where the water is cold and it has deep convections, and then they transport throughout the domain. They also go in at low latitudes, but this high latitude entry is what's being shown here. This model is climatologically forced, so it doesn't have interannual variability in the atmosphere. Okay, so I just thought it would be fun to look at this to see. So this is the upper North Atlantic deep water. This is if you went a little bit further down in the water column, you'd see more of a ribbon along the boundary. But if you read things by Susan Lozier and others in Science recently, that they talk about there being two paths, one in the interior and one along the boundary, for water that goes down into the, that is the cold water path of the Manila overtransformation. So just play that again. And
We listen to music for trip as well.
music? What am I doing here? Oh, not behaving. Wow. Oh, there we go. I'm not sure what happened, but anyway. So for some reason it's not showing anything. But you saw it once. You can come into my office and see it more. So I'll take questions now. Yeah.
If you took a much bigger box, I guess ocean atmosphere heat flux would be likely to play a bigger role, but you'd still have advection if you thought of the box as, say, the North Atlantic as a whole instead,
Right.
then I guess you'd have less subject to model ocean variability.
Right. So if you
But
looked
you'd still
at
have advection
Yeah.
being important.
Yeah, well, if you looked at that initial Trenberth and Karen picture that I said, over that latitude band that my box is, half a petawatt is coming out of the ocean to the atmosphere, and 0.2 petawatts is coming out in the Gulf Stream in that box I chose. So that gives you an idea of the relative strength of the two. If you did the other box, you'd have some oceanic advection, but a lot of it would be controlled by Ekman advection, which is oceanic, but as far as the oceanographers are concerned, it's not sort of an active oceanic process. It's slave to the atmosphere and works on the background temperature gradients, as opposed to the Gulf Stream, which is really that the variability in the heat transport convergence is forced somewhere else. So yeah, I agree with you. If you did a bigger box, and you probably would get a more consistent answer, but it also would be less interesting to me as an oceanographer. So yeah.
So this thing about the in the low pass heat content
Uh-huh.
driving the heat fluxes.
Right.
I would just caution against you looking at a 3-month lag in the situation when you've done a low pass filter.
Yeah, I agree with
You're
you
mixing
totally.
information from the
Yes.
future and the past in that
Yes.
low pass filter. So yeah, you probably need to check that out.
Yeah, and I wanted to do summer versus winter.
Yeah.
Because if what I said was, if it was reemergence, then I'd see it in winter and not in summer. So I agree with you totally, that it's not, I can believe that it's anti-correlated, and the lag, I think, is, you're right, doing the low pass at 1 year. If I did it for 2 years, which I didn't try, I'd probably get a different lag. But I think there is something there in terms of, my guess is the correlations will be big in winter and small in summer, but I haven't done that yet.
So you said earlier on that most of the models had the Gulf Stream too strong, at least on the upstream side. Does that mean the mass flux is too big, or the
No,
or
it's
the-
not
or
that they're
the
too
velocity's too?
It's not that they're too strong, actually. In the mean, it's too weak. And so it dumps its heat next to the coast, and then it's too cold downstream because it's not getting heat out into the interior. The interannual variability of sea surface temperature is too big. But that probably has to do with it being not stored deep enough. That's what my surmise was, and that was true in the Kershaw when we looked at it in more detail. I haven't looked at it in more detail in the Gulf Stream, but I suspect that it's just not stored deep enough. It's kind of, once again, more of a mixed layer, slightly below mixed layer feature in the models. But I'd have to prove that. But I do think that looking at those regions, it is an interesting place to do diagnostics of climate models. If we're really looking for robust decadal variability, and if the Gulf Stream or the North Atlantic Current is playing a role in that, to really diagnose how the variability in SST comes about, or heat flux, and whether it's consistent with higher resolution and with the observation. If you look at sea level, which is a measure of heat content, it's anti-correlated on low frequencies with the surface heat flux. So it's consistent with this. That anti-correlation, I think, is very robust. And what this tells us is how deep you have to go. Okay, yeah, Robin.
So all these models had similar vertical structure?
I didn't actually explicitly look at the vertical structure. I assume they do. I don't know. I haven't looked.
Because I was trying to think how that might affect the new climate runs, because some of them are adding more vertical structure or
Vertical layers.
levels.
Oh,
Levels,
yeah, I didn't write that down. Echo had more. I think it had 50 something. Mercator had 40, and Pop was less. Can't remember exactly how many. I could go look on my laptop and figure it
Yeah.
out. But I mean, I think it's horizontal resolution that's the problem, not the vertical resolution.
Yeah, it's just, I know that's one change that's happening in the ocean for these.
Yeah, because they're like, I know they're up to like 50 or 60 levels is what they're doing now.
40. I know the CCSM3, I think, had 25 or something, and then
Yeah, I'll have to go look. I think it's up to 40 or 50
right.
now for the CCSM4 low resolution. But that's not going to solve the Gulf Stream problem.
You won't really, depending on how you go fine.
I'm sorry?
You won't really, depending on having fine vertical.
No, I don't think
Oh,
so.
but I was just curious if they.
Yeah, no, Pop is definitely lower. And maybe that's related to the vertical pumping. I don't know. Yeah.
So would it be worth doing this sort of analysis in a climate GCM, do you think, or do you think the errors are so big that?
I think it would be interesting, and I actually have a proposal. There was a call from NASA to develop satellite-based metrics for the IPCC AR5, what is it, CMEP 4? 5. Again, the numbers are now synchronized, they weren't before. To develop like monthly sea level, monthly surface flux products that then you could do this kind of analysis in the climate simulations. You'd have them at your fingertips. And Young-Oh Kwan did do this kind of analysis in the Kuroshio, and he found that you did get this fluxing of heat out. But the sea surface temperature variability is too big. Whether that means that the atmospheric variability that would be in response to sea surface temperature would be too big is another question. So.
What I sort of think would be interesting to do would be to take a reasonably high resolution coupled model, which had something which looked more like the observed Gulf Stream, see what I mean, and then take the fields out of that model and take the ocean component out of that model and drive that ocean component in a similar way to these products. So, i.e., putting the heat fluxes in, using the bulk formula, and assimilating the data, and then seeing if you can actually retrieve what happened in the coupled model.
Yeah, and
some of these differences between the real world and the model could be due to the procedure that is used to force the
yes,
model.
absolutely. The Julie, Frank, various people, Frank Bryan, CC Betts, are all running coupled 10-kilometer ocean simulations right now. I want to get this published first, and then that is obviously a next step to evaluate, because then you'd have consistency,
Yeah.
and you don't with these. Although ECHO, whatever magic Dimitri does, seems to give you a pretty good representation. And it also says that if you want to do this kind of analysis, having a conserving assimilation system is really important. It's hard to do, but they're talking about doing adjoints at high resolution, which I'm kind of baffled how they're going to do that, but yeah. Go ahead.
I was just curious if, I'm fascinated by the frequency split that you've done. And I was wondering if you'd actually made a difference between a frequency filtering and a coarse graining. If you were to do like a 1-year running mean, every month, and then do this calculation, would you get the same results?
I did do something like that, and I got about the same thing, because I was really frustrated with it being so dependent on what the low pass was.
Right.
And so I did do a running mean, and I got the same answer, pretty much. The reason I took out the seasonal cycle is because in surface flux, it totally dominated by the seasonal cycle. And if you just low pass that, it doesn't really work.
Right.
So you have to take out the seasonal cycle first and then do some sort of magic. But I did try the running because I was sort of desperate, and I got the same answer. Yeah.
Of course, this is an extreme area, but if I'm right, the force behind Matt's suggestion is that all your fluxes here are really large compared with the sort of error that you can stand with, right?
Well, globally,
Yeah.
but locally you can accept, of course, much larger errors.
Yeah.
The errors on like the NSEP fields, you hear quoted 5 to 10 watts per meter squared, something like that. On interannual timescales, I don't know. That's sort of instantaneous. I don't know what it would be. And that's big. If you think about 10 watts per meter squared over 100 meters of ocean would raise it by something like, I did this calculation with 4 degrees C over a year, right? It's big.
And typically, if you do a flux adjustment in the Gulf Stream region, you're getting, plus 100 watts per meter squared in one grid cell and minus 100 watts per meter squared in another.
Which reflects this sort of low resolution error. Yeah.
It's just you can't resolve the front. Really.
Yeah. Well, thank you for your interest.
Thank you.
Yeah.